Welcome to this walkthrough of LeetCode problem number 65, valid number. In this problem, we'll explore how to determine if a given string adheres to specific formatting rules to represent a valid number. We'll break down the approach step by step to help you master this concept. Let's get started. In this problem, you are given a string s, and the goal is to determine if it represents a valid number. A valid number can include several components. First, there are digits, which are simply one or more numeric characters, such as 123. Next, there is the decimal point, represented by a period, which divides the integer and fractional parts of a number. A decimal number is valid if it has digits either before, after, or on both sides of the decimal point, for instance, 12.34, 0.5, or 3. However, a decimal point by itself with no digits, like dot, is not valid. Then, we have the exponent, an optional part of the number denoted by e or e, followed by an integer. This is commonly used in scientific notation, such as 1 times 10 to the power of 10 or minus 2.5 times 10 to the power of negative 3. Finally, a valid number can have an optional sign, either plus or dash, which can appear at the beginning of the number or immediately after an exponent. Examples include minus 123 or plus 6.78 times 10 to the power of negative 4. For the string to be considered valid, it must only contain these components, follow the proper syntax, and not have any leading or trailing spaces unless those spaces are trimmed. If the string meets all these criteria, we return true, otherwise, we return false. The input to the problem is a single string s. This string may include digits, a decimal point, an exponent character, e or e, optional signs, plus or dash, and spaces. The output is a Boolean value, true if the string represents a valid number and false otherwise. For example, if the input is s equals 0, the output is true. This is because the string 0 represents a valid integer. Another example is s equals 0.1, where the spaces are ignored, and the resulting string 0.1 is a valid decimal number, so the output is also true. Now, consider the input s equals abc. In this case, the output is false because the string contains invalid characters that are not part of a valid number. Similarly, for the input s equals 1, the output is also false. This is because the string contains a space followed by the letter a, which is not allowed in a valid number. On the other hand, if the input is s equals 2e10, the output is true. This is a valid example of scientific notation, where 2 times 10 to the power of 10 represents the number 2 multiplied by 10 raised to the power of 10. Let's look at another example. If the input string is s equals -90e3, the output is true. This is because the string represents valid scientific notation. Specifically, minus 90 times 10 cubed corresponds to the number minus 90 multiplied by 10 raised to the power of 3. However, for the input s equals 1e, the output is false. The reason is that the exponent e must be followed by an integer, and in this case, it is not, making the string invalid as a number. There are a few constraints and edge cases to keep in mind. The length of the input string s must be between 1 and 20 characters. Additionally, the string will only contain printable ASCII characters. Any leading or trailing spaces should be ignored when determining if the string is a valid number. Importantly, the string will not include non-numeric symbols such as $ or %. For edge cases, a string with only whitespace, such as, is not valid. Similarly, strings consisting only of a decimal point or an exponent, such as dot or e, are also invalid. Furthermore, strings with multiple decimal points or multiple exponents are invalid. For example, 1.2.3 or 2e3e4 cannot be valid numbers. On the other hand, valid scientific notation examples include 2 times 10 to the power of 10, which can optionally include a sign, such as minus 3 times 10 to the power of negative 2. Decimal numbers are also valid with or without leading or trailing digits, such as 0.5 or 2. To summarize, the solution must handle all these cases to correctly determine whether the input string represents a valid number. Let's continue with the next part. To solve the valid number problem, we need to validate whether a given string conforms to specific formatting rules for numbers. This involves parsing and carefully handling edge cases, such as optional signs, decimal points, and scientific notation. One approach we could use is a brute force method with regular expressions. Here, we craft a regex pattern that captures all valid number formats, such as integers, decimals, and numbers with exponents. While this method is concise and directly matches the problem's rules, it comes with significant challenges. Writing a regex for such a complex problem can be error-prone, difficult to debug, and hard to maintain, especially if new constraints are introduced. Additionally, for very long strings, regex matching can be inefficient due to its overhead. So while it's appealing in its simplicity, the downsides of using regex limit its practicality for this problem. Another approach is to use a finite state machine, or FSM. This involves designing a set of states to represent different parts of a valid number, such as the integer part, fractional part, or exponent part. The transitions between these states are determined by the current character being processed, such as digits, a dot, or an e. At the end, we check if the final state represents a valid number. This method is robust and systematic, making it easier to debug and extend compared to regex. However, it requires careful planning to define the states and transitions, and the implementation can become more complex. A third approach is manual parsing, where we parse the string character by character, validating each component explicitly. This involves splitting the string into parts, like before and after an e, and validating each segment independently. While manual parsing gives complete control and can be optimized for specific edge cases, it often results in unstructured code that's harder to maintain. Among these approaches, the FSM stands out as the most structured and reliable solution for this problem. The FSM approach becomes even more appealing when we consider some key observations about the problem. A valid number can be broken down into three main components: the integer or fractional part, the optional exponent part, and the optional sign. Each of these has clear rules that can be effectively modeled using states. Edge cases, such as trailing spaces, multiple signs, or missing digits, are handled more systematically with FSM transitions than with regex or manual parsing. For example, invalid scenarios like multiple occurrences of the character e or a misplaced decimal point can be addressed directly within the FSM state design. When comparing the trade-offs, FSM offers better readability and debugability than regex, and it's more structured than manual parsing. All approaches share the same linear time complexity, O(n), where n is the string's length, but FSM has a lower constant overhead compared to regex, making it more efficient in practice. FSM is the clear choice for this problem because it balances clarity, robustness, and maintainability. Its systematic handling of edge cases through well-defined state transitions ensures that the solution is both comprehensive and easy to extend. This is particularly important for a problem like this, where multiple components and constraints interact in complex ways. By defining explicit rules for valid transitions, FSM reduces the likelihood of missing edge cases and creates a solution that is not only reliable but also easier to debug and modify. This makes FSM the most practical and effective approach for solving the valid number problem. In this problem, we need to determine if a given string represents a valid number. A valid number can take different forms, such as integers, decimals, or even scientific notation like 2 times 10 to the power of 10. The difficulty comes from handling various edge cases, such as strings with spaces, multiple decimal points, or invalid formats like E1 without a number before it. To solve this, we start by trimming any leading or trailing whitespace from the string. This is important because spaces are not meaningful in the context of a valid number. For instance, a string like 123 should be reduced to 123. If the resulting string is empty after trimming, it means there's nothing left to validate, so we immediately return false as it cannot represent a valid number. Once spaces are removed, we focus on handling scientific notation, which uses E or E to separate the base and the exponent. A valid scientific notation must have a number, either integer or decimal, before the E and an integer after it. We split the string on E or E to isolate these parts. If the string contains more than one E or none when it's required, it's invalid. After splitting, we validate the part before E as a decimal or integer, and the part after E strictly as an integer. For decimals and integers, we must ensure there's at most one plus or dash sign at the start, only one decimal point if it's a decimal, and the rest of the characters must be digits. Some special cases to handle here include formats like 123.123 or 0.0, which are all valid decimals. When validating the exponent part, it's important to remember that it must be a valid integer. This means it can start with an optional plus or dash sign, but the remaining characters must all be digits. Cases like e+, e1.5, or a standalone e are invalid because they fail to meet these criteria. Beyond the exponent, there are other edge cases to handle as well. For example, an empty string should immediately return false. Similarly, strings with multiple signs, like ++1, or multiple decimal points, like 1.2.3, are also invalid. Standalone characters like e, but, or dash do not represent valid numbers either and should return false. Breaking the problem into smaller parts makes it easier to handle. Splitting on e allows us to address the base and the exponent separately, simplifying the validation process. For decimals, the rule is straightforward: there can be at most one decimal point, and digits must exist either before or after it. Signs like plus or dash are only allowed at the start of a number or the exponent part, ensuring proper formatting. Finally, after accounting for signs and decimal points, any remaining characters must be digits. These insights, combined with string manipulations like trimming and splitting, form the foundation of our approach. Additionally, we can use simple Boolean flags to keep track of whether we've encountered a decimal point or a sign, making the implementation more efficient and organized. The time complexity of this algorithm is O(n), where n is the length of the input string. This is because we process each character at most once during operations like trimming spaces, splitting on e, and validating the parts. The space complexity is O(1), as we don't use any additional data structures apart from a few variables to track states. Let's look at an example to see how this works. For the input 2 times 10 to the power of 10, trimming spaces leaves it unchanged. Splitting on e gives us 2 and 10. We validate 2 as a valid integer and 10 as another valid integer, so the function returns true. This demonstrates how we efficiently handle the structure of a valid scientific notation. For the input -90 times 10 cubed, trimming spaces gives -90 times 10 cubed. Splitting on e results in -90 and 3. Both -90 and 3 are valid integers, so we return true. On the other hand, for a string like 1.2.3, trimming spaces doesn't change the input, and since there's no e, we validate it as a single number. However, it's invalid due to multiple decimal points, so we return false. For E9, trimming spaces gives E9, and splitting on e results in an empty left part and 9 is the right part. The empty left part is invalid, so we return false. These examples highlight how the algorithm handles both valid and invalid cases systematically. Here, we start by defining a class called solution with a method isNumber that takes a string s as input. Inside this method, we define two helper functions, isInteger and isDecimal. The isInteger function checks if a given string represents a valid integer. It first ensures the string is not empty, then checks if the first character is a plus or dash sign, which indicates a signed integer. If so, it removes the sign and verifies if the remaining part consists only of digits using the isDigit method. Next, the isDecimal function determines if a string represents a valid decimal number. It first handles optional leading plus or dash signs, then checks if the string contains a decimal point. Using the partition method, the string is split into 3 parts: the integer part, the dot, and the fractional part. The function ensures that at least one of the integer or fractional parts is valid and consists only of digits, while allowing the other to be empty. If all these conditions are satisfied, it returns true. At the end of this slide, we strip any leading or trailing whitespace from the input string s and check if it contains the character e or e, which indicates scientific notation. If the string contains e or e, it is split into 2 parts, the base and the exponent, using the partition method. The base is the part before e or e, and the exponent is the part after it. The method checks if the base is either a valid integer or decimal number by calling the appropriate helper functions, and ensures the exponent is a valid integer. If both conditions are met, the method returns true. Otherwise, if the string does not contain e or e, it simply checks if the entire string is either a valid integer or decimal using the same helper functions. This ensures that the input string conforms to the rules of a valid number, covering integers, decimals, and scientific notation. Here, we start by defining the main class and method, isNumber, which takes a string input s and determines if it represents a valid number. Inside this, we see the helper method isInteger, which checks if a given string is a valid integer. It first handles the case where the string is empty, returning false. Then, it checks for an optional leading plus or dash sign and removes it for further validation. Finally, it ensures the remaining characters are all digits using chars.allMatch, character isDigit. Next, we have the isDecimal method, which validates decimal numbers. Like isInteger, it starts by handling empty strings and optional leading signs. It then looks for the presence of a dot using index of _. If no dot is found, the method returns false, as a decimal must include a dot. The string is then split into two parts, the integer part before the dot and the fractional part after it, preparing for further checks. The isDecimal method continues by addressing edge cases. If both the integer and fractional parts are empty, it returns false, as a valid decimal needs at least one numeric component. It then validates each part individually, ensuring that the integer part, if not empty, contains only digits, and the same for the fractional part. If both checks pass, the method returns true, confirming the string is a valid decimal. Moving back to the main isNumber method, the input string s is first trimmed to remove any leading or trailing whitespace. If the trimmed string is empty, it returns false. Next, it checks for scientific notation, which is denoted by the presence of e or e. If found, the string is split into two parts, the base and the exponent. The base must be either a valid integer or decimal, and the exponent must be a valid integer. If these conditions are met, the method returns true. Finally, if no scientific notation is detected, the method checks whether the input string is either a valid integer or a valid decimal using the helper methods isInteger and isDecimal. If either of these checks passes, the method returns true, confirming that the string represents a valid number. Otherwise, it returns false. This implementation ensures that all edge cases, such as optional signs, empty parts, and invalid characters, are handled effectively, making it robust for determining the validity of numerical strings. Here, we begin by examining the input string 2e10. First, we strip any leading or trailing spaces, but since there are none, the string remains unchanged. Next, we check for the presence of the character e or e, which indicates scientific notation. In this case, the string contains e, so we split it into two parts, the base, which is 2, and the exponent, which is 10. To validate the base, we call the isInteger function with the input 2. Since the first character is neither plus nor dash, we check if the entire string is numeric by using isDigit, which returns true. This confirms that the base is valid. Now, we proceed to validate the exponent by calling isInteger with the input 10. Again, the first character is neither plus nor dash, and isDigit confirms that 10 is numeric. Since both checks pass, the base and the exponent are valid, and the function returns true for this input. In this example, the input string is -3.14. After stripping spaces, the string remains unchanged. Unlike the previous example, this string does not contain e or e, so we proceed to validate it as either an integer or a decimal. Since it contains a decimal point, we call the isDecimal function with the input -3.14. The first character is a dash, so we remove it, leaving us with the string 3.14. This string contains a dot. So we split it into two parts, the integer part, 3, and the fractional part, 14. We check each part using isDigit, and both 3 and 14 are confirmed to be numeric. Since both the integer and fractional parts are valid, isDecimal returns true. This means the input string is a valid decimal, and the function returns true for this input. Now, let's look at the input string ABC. After stripping spaces, the string remains unchanged. Since it does not contain e or e, we try to validate it as either an integer or a decimal. First, we call the isInteger function with the input ABC. The first character is not plus or dash, so we check if the entire string is numeric using isDigit. This returns false, meaning it is not an integer. Next, we call the isDecimal function with the same input. Since the first character is neither plus nor dash, we proceed to check for a decimal point. The string does not contain a dot. So isDecimal immediately returns false. As the string is neither a valid integer nor a valid decimal, the function concludes that the input is not a valid number and returns false for this input. To begin analyzing the time complexity of our solution, let's break it down step by step. First, we have the string stripping operation. The strip function scans the input string s to remove any leading or trailing whitespace. This requires examining each character in the string, resulting in a time complexity of O, n, where n is the length of the string. Next, the partition function is used to divide the string around the first occurrence of e or e. This also involves scanning the string, and in the worst case, it may need to traverse the entire input, which again results in O, n, time complexity. Together, these operations prepare the string for further validation efficiently. Now, let's discuss the time complexity of the helper functions, isInteger and isDecimal. For isInteger, we check for an optional sign at the beginning and validate that the remaining characters are digits using isDigit. Since isDigit scans the substring once, the time complexity is O, k, where k is the length of the substring being checked. In the worst case, this could be the full length of the string, or O, n. For isDecimal, we handle an optional sign, partition the string on the decimal point, and validate both the integer and fractional parts. The partition operation takes O, k, and the subsequent isDigit calls for the parts together also take O, k. This makes the total time complexity of isDecimal O, k, with the worst case again being O, n. Lastly, when validating the presence of e or e, we compute both the base and the exponent using these helper functions. Since each validation is O, n, in the worst case, this step remains linear in time complexity. Bringing it all together, the overall time complexity of the solution is determined by the dominant operations, which include the initial strip, call and the validation processes using isInteger or isDecimal. Each of these operations runs in O, n, time, and since they are performed sequentially, the total time complexity remains O, n. Now, turning to space complexity, the strip and partition functions do not create new copies of the string but instead return references to substrings. These operations are performed in constant space, or O1. Similarly, the helper functions like isInteger and isDecimal use only a fixed amount of memory for intermediate variables, and no additional data structures are used. This ensures that the space complexity of our solution is O1. With the fundamental time and space complexities established, let's consider how the solution performs under different scenarios. In the best case, when the input is trivially valid, such as a single-digit integer like 5, the function performs minimal checks, with the strip operation dominating at O, n. In the average case, for inputs like 3.14 or 2 times 10 to the power of 10, the function executes partitioning and validation steps, which together still result in O, n, time complexity. Finally, in the worst case, for large and complex inputs like -123.456 times 10 to the power of 789, the function still performs O, n, operations due to the strip and validation steps. Importantly, space usage remains constant across all cases, as no additional memory is allocated beyond the fixed size variables. To conclude, let's compare this approach to a brute force or naive solution. A naive approach might involve iterating through the string character by character, manually checking validity. While this would still result in O, n, time complexity, it would likely require additional space for intermediate data structures, making it less efficient. In contrast, the optimized solution we've discussed leverages Python's built-in methods like strip, partition, and isDigit to perform the necessary operations concisely and efficiently. This approach achieves both the optimal time complexity of O, n, and space complexity of O, 1. Finally, the proof of Big O stems from the fact that all key operations, such as strip and partition, are linear in the size of the string, and no unnecessary nesting or repetition occurs. The solution is both elegant and computationally efficient, making it well suited for this problem. One common mistake when validating numbers is failing to handle leading or trailing spaces. For example, strings like 123 or 3.14 are valid numbers, but they need to be trimmed of spaces before validation. If this step is neglected, your implementation might incorrectly reject valid inputs. Another issue arises with exponents. Strings like 1 times 10 to the power of 5 or -2.3 times 10 to the power of -4 are valid, but they require digits both before and after the e. Errors occur when inputs like E5 or 1E are mistakenly marked as valid. Similarly, decimal placement rules can be a source of confusion. Numbers like 3 or 0.5 are valid, even though they lack digits on one side of the decimal point. Misunderstanding this can lead to incorrect rejections. Finally, handling signs correctly is critical. Positive or negative signs are valid at the start of the number or immediately after the E, but invalid inputs like -+3 should still be rejected, while valid ones like -2 times 10 to the power of 5 need to be accepted. Misclassifying these can lead to subtle bugs in your implementation. Edge cases are another major challenge. For example, empty strings, single dots, or inputs with multiple E characters, like 1E2 E3, can all lead to bugs if not explicitly addressed. During interviews, these edge cases are often where candidates are tested most rigorously. Inputs like 0E, 3E.5, or 5E- are designed to evaluate how thoroughly you've handled these scenarios. When implementing solutions, you might use regex for simplicity, but an iterative parsing or state machine approach can demonstrate deeper understanding. These methods are especially valued because they showcase your ability to handle edge cases and complex rules. Also, remember to discuss time complexity. Parsing a string is typically O, n, where n is the length of the string. Be ready to explain this analysis and highlight trade-offs between performance and code readability. Lastly, don't forget to ask clarifying questions when given the problem. For instance, confirm whether scientific notation like 1 times 10 to the power of 10 is allowed. This ensures your implementation aligns with the expectations. This problem ties closely to several related challenges. For instance, LeetCode's number 8, string to integer, etoile, involves parsing and validating strings with specific rules. Similarly, number 20, valid parentheses, tests your ability to enforce structural correctness, while number 468, validate IP address, and number 10, regular expression matching, push you to handle intricate patterns and edge cases. When considering alternative approaches, regex-based validation is a quick and concise option, but it can be difficult to debug and maintain, especially with tricky edge cases. On the other hand, state machine parsing offers robustness and is particularly useful for handling complex rules, though it requires more effort to implement and test. Finally, iterative character-by-character validation provides fine-grained control and is easier to debug, but it can lead to verbose or error-prone code if not carefully structured. Each approach has trade-offs, so choose the one that best balances clarity, performance, and maintainability for your specific use case. Great job! To recap, we tackled the valid number problem by exploring string parsing and validation techniques while handling edge cases like decimals and exponents. These skills are essential for solving similar problems effectively. Thanks for watching, and don't forget to subscribe for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!